Hi, everyone. My name is David Madison. I'm the director of NISS, the National Institute of Statistical Sciences, and I'm also a professor at Cornell University. So I'm very excited today about the launch of a new event series, but before we get there, I just wanted to briefly remind everyone that the NISS Co-Laboratory has now launched. So the NISS Co-Laboratory is really about strengthening efforts to bring different communities in our profession together and to reach out to interdisciplinary communities as well. The co-laboratory has a handful of strategic aims that we try to push for. Overall, NISS tries to partner to strengthen ongoing research and training activities to avoid duplication, but take the lead when there's critical but unmet needs or as important emergent topics arise. So one of the first big pushes in a long-running research program of NISS is Statistics Serving Society. This takes different forms, from virtual meetups to in-person Ingram-Occam forums that we hold every year. So upcoming events include a series on the opioid crisis and reducing maternal mortality rates across the US. We are launching a new researchers network at NISS. This is an outgrowth of the very successful graduate student network. So the graduate student network's not going away, it's just growing. So we're trying to put several of the new researcher activities that NISS does under one umbrella. So this includes the writing workshop we do every year, virtual career and grad school fairs, the graduate student research conference that's run and hosted by graduate students for and by themselves, as well as a new initiative on capstone projects connecting academic students with industry and government. A big thrust is the intersection of AI and statistics as well. Today we'll be talking about AI statistics and data science in practice, but we've also spent an enormous effort integrating statistical and AI sciences in federal government through a web event series, as well as AI Day last May at the National Academies of Science. Collaborative Data Science is another new series that we'll be launching soon. This is to celebrate collaboration between statisticians and data scientists and engineers of all kinds. So look for more information in the coming month. Public health and the environment is another thrust. Here we consider the importance of data-driven decision-making at the intersection of public health and environmental crises such as climate change. Finally, data visualization has been a long-running strength of NISS, and we hope to renew this in the coming year. Look for new graphics and design competitions in the spring. So with that, I'd like to introduce Nancy McMillan, who's the chair and moderator for today's session. She's also the chair of the NISS Affiliates Committee. Nancy? Nancy, go ahead and unmute quick.
Okay, thank you, David, and welcome everybody to our first presentation in our new series, AI Data Science and Statistics in Practice. This series is part of the NISS Collaboratory that David was just introducing, and it's going to bring together leading experts from industry and academia, such as our speaker today, to discuss the latest advances and practical applications in AI data science and statistics. So each of our sessions is going to feature a keynote speaker on cutting edge topics where attendees can engage with the speaker on the challenges and opportunities in applying these technologies in real world scenarios. The series is intended for professionals, researchers, and students that are interested in these topics, and is going to offer insights into various applications in both research fields and industry, providing theoretical insights, practical examples, and discussion issues. So as we provide the presentation today, please put any questions that you have into the chat. I'm going to be providing those to Professor Yu during the talk, so you won't have to wait till the end. We'll try and introduce some as we go at breaks in her presentation. So with all of that, we're very excited to have Professor Yu as our first speaker in this series. This is our first session, and we're going to be having these sessions monthly moving forward from here. Professor Ben Yu is the class of 1936 second chair in the College of Letters and Sciences, and Chancellor's Distinguished Professor, Department of Statistics and Electrical Engineering and Computer Sciences at the University of California at Berkeley. Professor Yu is a statistician by training, but her research interests and achievements extend well beyond statistics. Her current research focuses on practice, algorithm, and theory of statistical machine learning and causal inference. She and her group have leveraged new computational developments to solve important scientific problems by combining novel and interpretable statistical machine learning approaches with domain expertise of collaborators in neuroscience, genomics, and precision medicine. They also develop relevant theory in these areas. Professor Yu's past work includes empirical process theory, information theory, Markov chain Monte Carlo methods, signal processing, machine learning, and high-dimensional data inference. Clearly a celebrated researcher in our field. She's a member of the U.S. National Academy of Sciences and a fellow of the American Academy of Arts and Sciences. She was the Guggenheimer Fellow in 2006 and the Tukey Memorial Lecturer of the Bernoulli Society in 2012. She was the president of IMS in 2013 to 2014 and the Ritz Lecturer of IMS in 2016. She received the E.L. Scott Award from COPS in 2018 and was the Bremen Lecturer at NeurIPS in 2019. So Professor Yu's talk today is on her book, which she shared with us a few minutes ago, was just published today. So congratulations, Professor Yu. Veridical Data Science, the Practice of Responsible Data Analysis and Decision-Making. We're all going to learn a bit about predictability, computability, and stability, and how these core principles for trustworthy data insights can be integrated into the data science lifecycle today. So with that, I want Professor Yu to please share your insights today with us, and I'll move to the side here. Thank you.
Thank you, Nancy, for the very generous introduction. So as Nancy said, I'm talking about really work with my team and collaborators for the last 10 years. And I really welcome questions during the talk. I have a pretty long expected time for the talk, so please do put in questions in the chat box so Nancy can help bring my attention. So veridical data science is a term actually attribute to a colleague, Tian Zhang from Columbia University. It means truthful, and I'll try to elaborate exactly what I mean by truthful. And it's really an attempt. The framework was developed very much from the research side, and I've been bringing to my classroom teaching. So over the last 10 years, I really evolved into this both education framework and the research framework, and it's still evolving. So this is not something set in stone. It's really philosophical and also practical, and had a lot of rooms for people to further develop and also to use it in particular contexts using domain knowledge. Data science is really a field right very much behind AI. We use algorithms and leverage domain knowledge and make decisions and generate new knowledge. And computing is at the heart. We cannot do anything mostly without computing. It's not the only thing, but it's very much core to today's practice of statistics and data science. And data science doesn't happen in one step, as most talks seem to, we kind of end up with this format, talk about algorithms. It's really a whole process. And earlier, statisticians like Box and Nelder and Cox talked about statistical investigation process. And it's really now called by computer scientists, data science lifecycle. And there are many, many people in the process making judgment calls, and often end up with what Goldman and Locken called the garden of forking paths, right? There's just many decisions and you can take different routes and you might end up different conclusions. So just to be more concrete, which data do you use? Actually, before that, what problem you try to solve? That's for like, what's the domain problem? And what data have been cleaned differently by a different person, do you get different results? If a different method or algorithm have been fit to generate a predictive algorithm, and you can continue on and on, right? If you do different visualization, both in the EDA stage before the formal modeling or after the formal modeling, do you have different impression? Would you choose different things to communicate? So all of this just humans making judgment calls, and they're all reasonable, and hopefully people have been documented. And uncertainty quantification has been at the center of statistics and also data science and AI. Because if we don't have trustworthy uncertainty quantification, we can mislead people and waste resources, and also could do harm, especially in medical domain at work a lot, right? If you believe something is really trustworthy and start having a surgery on somebody, even though the recommendation actually have a huge uncertainty, then you might do harm. And currently, most statistical practices concentrate on one source of uncertainty, which is when you have a very good stochastic generative model and have decades of history and research to kind of know more or less how to do uncertainty. Even there are still research to be done. But there are other important sources of uncertainty that we need to take into account, bring in to the consideration formally instead of informally, so that we don't underestimate uncertainty and achieve better trustworthy uncertainty quantification. Right now, most of the time, I think we're underestimating uncertainty because if you look at the whole pipeline, we're only looking at one part. So veridical data science was proposed informally in 2020 paper with my former student Carl Kuhnbeer with at UCSF. It's a philosophical conceptual framework for practicing data science responsibly with a documentation requirement. So it's really a response to the replication crisis, which got a lot of attention about 10, 15 years ago. It's a framework for producing trustworthy data-driven results and critically assessing the trustworthiness of data-driven results in the context domain science and reality. So veridical really is an English word. It's rarely used, but it's a proper English word, means truthful and coinciding with reality. So for the rest of the talk, I want to go a little deeper about the motivation for replication crisis, why that motivated the veridical data science, and then go to the book that's just, as Nancy said, being published by MIT Press in the machine learning series. Actually, today is the official publication date. And then I'll go to some case studies to really show the value added to two medical case studies. And now I will finish with ongoing work, which already started in chapter 13 of the book, on PCS uncertainty quantification. Actually, any questions at this point? No, okay.
Not yet.
Not yet. So let's just concentrate on, for now, a prostate cancer detection problem, right? This is pretty standard machine learning or statistical problem. You can call classification, you can call unsupervised learning, but prostate cancer is leading cause of cancer deaths in the developed world. The life occurrence of prostate cancer for men is about the same 12–13% as breast cancer for women. And currently we have a clinical test called PSA, prostate-specific antigen test, use one protein, KLKS. But the AUC, the area under the curve, is not very high, it's 60%. For the people who will be set to do invasive biopsy. So that incurs pretty high false positive, and the biopsies for prostate cancer detection, it's actually quite painful. So can we do better? Let's keep this in mind. And this is really a continuation of this oncology replication crisis. Right? This is related to cancer research. And even today, 10, 15 years after these two papers from two companies, Amgen and Bayer Healthcare, they reported low replication rates, 12–13%, and landmark findings in preclinical oncology research. So this is more related to clinical trial, but still it's in the general cancer research domain, and we're still struggling to do better. So it's not like we solved the problem, we got attention, but I think one problem we can fix is to broaden our consideration uncertainty sources so we don't underestimate as much as we do. So yeah, house uncertainty, I think that's what statisticians and data science and machine learning also turning attention to uncertainty quantification. Data cleaning is a major source of uncertainty we need to take into account. And the other is team effect of different people making reasonable choices to choose different algorithms, and you end up getting different conclusions. So we did this data cleaning project to bring the message home why data cleaning cannot be ignored anymore. Most people who do really code surface apply work will agree like 60 or even 80 or 90% effort usually goes to data cleaning. But then we just pretend it's not there and then we go on. So we did this experiment in my class 3 years ago. This is the people who helped me, my TA, my former student, and then Complance is ER doctor from UCSF. With Aaron's connection, we got teams of UCSF medical doctors to work with the students. So we have some expertise. And this is emergency room medicine or ER. We want to know traumatic brain injury, whether a kid in the clinical, in the ER room should be sent for CT scan or not. Because if you send too much, this radiation for young kids, there's a lifelong harm could be done. So we really care about sensitivity and specificity. So the 3 teams end up with 3 different versions of the clean data. And Omar, they were giving the same instructions. And I told them not to talk to each other. So there was no spilling of using the same thing. And Omar really just made his own reasonable calls. And we got like 10 clean data sets. And roughly, we see 10% of sensitivity up and down. And that's what you get if you bootstrap one clean data set, right? So this is saying that the uncertainty for this problem with these people who clean the data, uncertainty is comparable to bootstrap. That's what a major source of uncertainty we consider. So that means I hope this make it for some cases that we cannot ignore the uncertainty quantification.
Professor Yu, we have our
Yes.
first question.
Yes, please.
Thomas Johnson asks, have tools such as targets, meaning R packages for reproducible pipelines, Jupyter notebooks, and sharing GitHub repos or code repos assisted with reducing the severity of the reproducibility crisis? And this was asked before you got to the data cleaning slide, so I think it was not specific to data cleaning.
Are they like pipelines?
So,
Is that the question?
well, tools such as R package for reproducible pipelines, Jupyter notebooks, and sharing of GitHub repos and code repos. So have some of the tools that data scientists are using to share their code and to do things more similarly helped with the reproducibility crisis?
I think so, but I haven't seen any systematic studies. That's my impression by talking to people in social science, for example. They have been doing pre-registration studies, just talking to people leading this transparent research from Berkeley. I get a sense that yes, it's improving, but I haven't seen a systematic measure of how much we have reduced. I would think that yes, but there's no, I don't see any systematic study to know how much. That's my impression, just by talking to people and just attention we're paying.
Thank you. Please keep questions coming to the audience.
But a negative news is that the reason I ended up working with cancer researcher is I visited the Hutchinson Cancer Center 2019 and gave an early version of this talk. And the validation center director, Ziling Feng, approached me and said that I think your framework would be useful for cancer biomarker detection. What he was facing even in 2019 was that people publish papers and everything has to be reproduced. And the replication rate by his center on cancer biomarker discovery is less than 10%. So in that particular area, things haven't improved. I don't know what's before, but if you use the rate I mentioned to you from the 2 paper 2010s, there didn't seem to improve. So that's why the last 5 years I've been working with cancer researchers and making inroads. So we got invited last year to do a software package for cancer detection and with my former student Tiffany Tan and former postdoc Anna Kenny, we put in a proposal. So if you got that grant, we can make a bigger difference in cancer detection. But that took 5 years just to get into the community, be recognized, be trusted. So we haven't heard from the result yet. Yeah, I would think that things improve, but I cannot say how much in cancer research. I think still very problematic based on the data I heard from Validation Center from Hutchinson Cancer Research.
Thank you. Another audience member, Jeff Sherifoff, said this climate models and this climate models uncertainty is hugely important with negative impact now to California homeowners. So thank you. So I think he's just stressing how important this uncertainty that's not being captured is.
Yes, I actually now have a project we have been working for the last couple of years on climate science too. Really haven't gotten to the uncertainty part. It's more on the part of just getting the prediction. So this is a plot taken from IPCC report from 1990. And this plot is to project the global temperature rise 100 years from 1990. And this is not posterior path from a single model. This is 9 different models from 9 leading groups. And you can see the prediction varies from 1.5 degrees to 5.5 degrees. And this is a huge, significant, not statistical significant. We don't have really, we haven't done any statistics, but this is substantially significant difference between 1.1, 1.5, and 5.5. And in terms of the recent hurricanes, we have been saying, right, what I'm reading from the newspaper is that we're having more frequent extreme weathers. And the home insurance, there was a particular report that the assessment of risk, particular in North Carolina, a certain area, I think near Asheville, were underestimation. But to be able to really predict the future, we something has to be stable. So if the whole system just changes very rapidly, it makes it very, very difficult for us to do a good job with uncertainty quantification. Therefore, there's fundamental difficulties in the science, in the physical system, which is evolving. Therefore, for the uncertainty from data cleaning, it's actually that part's under our control. Hence, there's no reason for us not to put that in. Right? Even you do that, we might still underestimate because the system is changing, can get into a phase transition or something like what happens with stock market. Oh, the prediction model will fail when you have a crash of stock market because the whole regime changed. So that is kind of a little bit, well, not a bit, a lot of time out of our control when something we don't understand. But what I'm saying that there are things we can do and we should do that. So thank you for the comment to bring the attention to climate science. So this is basically different humans from different teams make different judgment calls. They basically based on the same physics, PDEs, and they all use data, but just use data in different reasonable ways. They are including IPCC. It's because they are aligned with humans, some group of humans, right? So actually, I'm giving a talk at the Simons Institute on Wednesday. I should probably put in a plug for that later about AI alignment in medical AI. And this is alignment with humans. This is the leading climate scientist group. What does it mean, the uncertainty here? This is not sampling. This is real uncertainty, but doesn't fall into the traditional framework. And 2016, right? This is self-selected, 1,500 scientists. But 70% of them said that they have tried and failed to produce another scientific experiment. More than half have failed to reproduce their own experiments. So I think most people find this not acceptable. 2022, 73 independent research teams work on the same data, no data cleaning worried, to test the same prominent social science hypothesis about the impact of immigration on support for social policies. And they get results all over the place. And in the title, there's a hidden universe of uncertainty. So as a statistician or data scientist, when you see such a title, I hope we said, well, it's our professional responsibility to at least review some of the hidden uncertainties. There's always unknowns, but now I'm advocating that there are at least two major sources. Can we rally the community and to really change our pipeline and to really reduce the underestimation of uncertainty? It takes more work. Similarly, 2023, biologists did the same thing. They find the same effect size differences because of analytical decisions, the team effect in ecology, evolution, biology. This is all separate scientists publishing these papers. I feel like most of you agree with me that we have to face this. And this is just great motivating papers, which we have been trying to address for the last 10 years. I think the time is right because the scientists are really telling us in public, there's a problem with traditional statistical pipeline. So VDS is really trying to help us to think critically, guided by the three principles, but it's not a cookie cutter. You have to think in domain knowledge and use relevant theory. And so we collect evidence to posit answers to domain questions. And we need to do documentation. So we have done 10 years of research from my paper, single author paper called Stability, was actually the Tukey Award paper. No, the Tukey Award lecture paper. That was not the award paper. It was. Then now we took 9 years with my former student, Rebecca Butter, to put it in a book to make it unpack the 2020 paper into a form that's more accessible. So the book will be published today, and the online free version has been available since February. So you don't have to buy the book, and it's available. It's very generous at MIT Press. So the intent in the audience is, it goes really well with a traditional book. We try not to do too much overlap. So you have a really good stochastic model. Yeah, all the traditional books do really well, guide you what to do. We try to bridge the gap and to say that often that model is imagined. We don't do a lot of model checking. And then we need to worry about a lot of other things and do a stability analysis. And also this is for domain experts. It's very accessible and it's written in a very, I would say, understandable narrative. We start in the book about what's reality, right? Is this photo capture all the reality? Probably not, right? It's processed, the camera has a lot of processing. And if the data you get is very distorted already from the reality, then any method cannot really go back to a final resolution of the reality, right? In some sense, it's design trumps analysis. Design here means data collection, right? You cannot really solve problem with bad data. So we start with this mental picture with the students. Want people to differentiate. Data is approximation, and domain knowledge is on the vertical. It's always there. What's reality, what's not? Without domain knowledge, with some common sense, we cannot answer that question. And then we go to algorithms and models. And software engineer has really developed in a very positive way. In some sense, all the large language models, the ChatGPT does really well. One thing that's pretty well helpful is actually coding. But the algorithm embedding codes or in mathematical notation, they are mental constructs. Do not always capture reality, just like data don't always capture reality. And we should always keep the future data in mind or future problem in mind. People are going to use your algorithm for something. What's that something? Is that similar to what you have? If not, why do you think people should use it? And the future data should also imply what test data you set aside when you have the current data. So bring future in early. And they're human decisions. In medical domain, people's lives are impacted. It's not just paper writing. Paper writing is one step in the process to make responsible decisions. And when you have something worthwhile to communicate, it's a step in the process. It's not the goal. we often stop at paper writing, and that's too early. And that's really reducing our impact, especially when people don't read our papers. Software has to be there. If anything you want people to use, has to have a good software. It has to be code reviewed or red teamed. So back to this, right? It's a data science lifecycle. And we want to extract reliable, scientifically reproducible, right? There's also, sometimes people talk about reproducibility as computational reproducibility. Veridical data science have computational reproducibility as a prerequisite, but we want scientific reproducible results. And we recognize formally there are a lot of judgment calls, and we cannot pretend it's not there and under account for that uncertainty. And we need to critically assess the impact of this judgment calls in the context of domain problem. For that IPCC report, they only had 9 models. I'm sure there are more than 9 climate groups. In some sense, they're already following the PCS framework. P is really reality check. Originally, it's in supervised learning means prediction, but now in the book, we have expanded as a placeholder, like a stand-in for reality check. So basic good science, right? Those 9 teams probably passed the P, right? They are credible. They capture reality. And then they extended, they showed aggregated through stability. They just show all the 9 results for 100-year temperature prediction. So the 3 core principles of data science are predictability. It's really being expanded in the book as reality check. We started with supervised learning, so that's why, and taking from machine learning, but it's expanded. And we have to use effective, efficient computation techniques and including data-inspired simulations. Stability is a huge expansion, sample-to-sample variability. Includes that, but also includes other perturbations to the data science process, include data cleaning choices, reasonable ones, and you document, and human judgment calls on algorithms. You can also include choices on, David mentioned visualization. We know that if you choose different colors for the same data, you get different impressions. So we need some stability for the choice of visualization so that we don't misled by the particular choice of, we put red on something. Red just catches attention. If you don't put something in red, you won't see it. So you have to really, EDA also have these stability issues to address. So PCS or VDS, it's unification and synthesis, right? If you see a lot of ingredients I talk about, I cannot possibly reference all the work. It means it's great, you're doing some version of PCS already. For myself, of course, we did some, otherwise we wouldn't develop this work. But because we have this formal framework, we're more thorough, we're more systematic, and we're more speedy. Instead of have to figure it out, oh, how should we do this? It's just really more effective and efficient applying this guideline. It's still a lot more work to be done in any particular project, but we just have this landmarks very much clearly outlined. So predictability is really standing for reality check, right? As I said, 2020 paper was very supervised learning, but the book really embraced the broader definition. It's minimum. If you can do prediction, it's not capture, that's good prediction, it's reality, but if it doesn't do well prediction, it doesn't capture prediction, doesn't capture reality. And what's good prediction varies from problem to problem. For hard problems, you cannot expect 90% accuracy. For the cardiology problem I'll mention briefly, we can only do 55%, but that's still something you have to beat at least 50% at random toss. So predictability you can demonstrate by showing result reemergence in new future data. That's the best. That's what medicine uses, external validation. If you're not, you should split the data in different ways to try to mimic the future and to see the patterns reemerge with this different kind of arbitrary split, which mimic the future. Computability, you need computability. You need to work with computer, and you need to worry about all the CS, like storage, communication, like convergence, all of that. But we add data-driven simulation. We don't do enough data-driven simulations, which is at our disposal. If you look at physics, there's a whole field called computational physics, computational chemistry. But we have computation statistics. But you look at how we do simulations, much is left to be desired. We don't do enough simulations with real data. I think some database of benchmark data will be hugely useful for statistics, but we don't have such a benchmark. Actually, I was talking to somebody, and maybe I'll follow up with David. Maybe NISS will be a great place to host such a database of benchmarks. So we need sufficiency, and computation has to be available, and we need to do simulations. Stability is really a core ingredient of PCS. And that's where we did a huge expansion intellectually and philosophically than the first two, basically kind of expanded from machine learning. And we have many reasonable judgment calls, right? I'm sitting in my office, I have a phone next to me. If I drop, I think the iPhone doesn't break. It shouldn't break because there is some perturbation to the use of my phone. I go to the 10th floor of Evans Hall, I drop it, it probably breaks because it's not a reasonable perturbation. But for somebody who's special agent, whatever, spy, they might want to have a phone so sturdy that from very high places still stays. So that's the context. Decide what's reasonable judgment calls. And that's human decided. So I'm not removing human judgment calls completely. We want to document it and remove certain uncertainties from reasonable human judgment calls. And we want to perturb both in terms of cleaning and also subsampling or other ways of argument the data. Again, back to documentation. I cannot emphasize enough. To do a thorough PCS analysis, you have to take detailed documentation. So that's what I'm training my student in my class. I do a class applied statistics and machine learning. It's a first year PhD level class. And majority of my class come from outside statistics. And you want to record the different reasonable judgment calls. And we may try some too, to have some forking. And you can do R Markdown or Quartal or do Jupyter Notebook. Reproducibility is actually a form of stability, right? The best that somebody actually redo the experiment, another lab, recollect the data, and make sure that the conclusion holds. The second best is that you replicate your own result. Third, you just somebody read the code and say that, yeah, it seems okay, certify your results okay. Right, so this is a different level. At least you should do the third. So we implement a new policy in my group recently. All our codes are code reviewed by another member who hasn't been involved in the project. And this person will become a co-author in the paper because huge amount of work to review the code.
Professor,
yes.
This is my question. Are you going to be talking more about computability specifically, more on what you would recommend being done in data-driven simulations?
Yeah, we have a paper. I won't talk a lot, but I can mention it. We have a whole paper written on that, but I will mention it, but I don't think I will get there.
Okay.
Yeah.
That's just a piece I'd like to hear a little more about. Thank you.
Yeah. We're still revising the paper. So yeah, we'll be happy to share and get your input. So Veridical, now you've seen something, it really means, well, first, like the name from Tianzhen, was because I tried to seek truth. So that's the first meaning. The second is I also want to be truthful to the process. It's like what we do instead of, I feel like the current statistical analysis is not really truthful to the whole data science lifecycle. It's truthful to one step. Therefore, that's why we underestimating uncertainty. PCS intends to build trust in data results. So if we open the book, this is the online free version. And on the left, all the section numbers you click, you can open up on the right, right? You can see that we start from problem formulation, data exploration, and the goal of the book is to ask insightful data-driven domain questions, how to think critically about data in the context of questions being asked, how to clean and formulate data, how to structure analysis, and how to scrutinize the trustworthy results, and provide intuitive introductory range of common statistical machine learning algorithms. So we do introduce algorithm, but in a way completely embedded in case studies with the PCS overlay.
Professor Yu, we have another question from the audience. The
Yes, please.
concept of stability seems quite similar to the statistical concept of robustness. What are the similarities and differences?
Definitely it was related. The reason I didn't choose robust statistics because robust statistics has a particular meaning. The 2013 paper was really trying to bring the data perturbation together with the model perturbation together. But robust statistics in statistics has now a particular meaning. So I try to avoid that. And stability includes numerical stability, control theory stability, data cleaning stability. So it's an expansion of that. I hope I answer your question. And robust statistics also, particularly you do regression, you tend to stay with the same kind of linear models, and you might do L1, L2, but stability in this, we consider linear models, consider random forest, consider deep learning, they all can be considered together. A different class of models together, different structures. So it's expansion. Yeah, and taking into account data processing. So the book try to mirror practice with the data science lifecycle, and PCS is in every chapter, and its documentation, and it's comprehensive, and coaches critical thinking. Detailed difference, we move away from true model framing. I personally think that hasn't been helpful to start, there's a true model, and we don't talk enough at all. So how to arrive at true model. Actually, true model is never true because it's only approximation. Maybe in physics, we're close to have a true model, but all the problems I have worked with in the last many decades, they're just postulated models which are useful. So it's very confusing for students to hear just a true model, and we don't talk about what makes a true model. And we have a bunch of things and important missing link. And later have to say, actually, the true model is not true. There are many candidates for true models. It's just very confusing. We try to fill the gaps between X and Y and domain problem. You cannot solve the problem connect reality by assuming more X and Ys. We do teach traditional methods through case studies and to share how the judgment calls were made and encourage people to document. And we address two new sources uncertainty from data cleaning and model choices. We have 5 kinds of exercise: true and false, conceptual, mathematical, coding, and project. One thing I want to bring attention to that we talk about 3 different ways for setting aside validation and test set. We recommend 3 split: training, validation, and test. Test is never touched. Validation you can touch for hyperparameter tuning. Random split, you write a document why this is reasonable. You're basically thinking that the content, the data collection, that the different units are exchangeable. But for hospitals, for medicine, usually data come from different hospitals. And you should do group-based split, because in the future, if you want your algorithm to be in a different hospital, you should set hospitals aside. Or time-based, you predict the future, you might do both, group-based and time-based. So we put this very clearly, you should consider more than random split and use the domain knowledge, the future application of your algorithm to decide. The test should be the best proxy for you about the future. And we have 3 case studies. We kind of used more this, so everybody has some understanding. There's organ donation data, nutrition data, and housing data. And in when I teach, I use from my research group projects in my teaching. But for this, we want to be more accessible. And codes and data all available. And we actually, in chapter 3, we help you to learn about GitHub, because that's something has to be done in our teaching classes. So on data preparation, you can see that we really have this flow chart showing that we want multiple pre-processed data. So we can assess, at least have 2 clean copies and run downstream, and to see whether make qualitative difference to change your conclusion. If you do, you have to go back, either saying this data clean is not right, write a documentation about it, or you have to find ways to reduce the variability so they have more trustworthy result. So let me go to case study 1, which I mentioned. It's really a general methodology development. Actually, we're not calling the method in the last revision called PCS ranking. So remember, National Cancer Institute. And first, Ziding introduced me to Sam Hanash from MD Anderson. And we worked with Tiffany and Anna with that group and did pancreatic cancer detection. And we published a paper with many collaborators and published, and the editor of the editorial. So people were very happy with what we did. And we basically give the guidelines from PCS. We didn't actually do data analysis. Asan Azarizi did all the analysis about statistician. And then I was invited to give a keynote at the EDRN PI meeting last year, 2023, September. And I went to Ziding, I said, I want to go in with 2 case studies. We feel like it's not convincing with 1 case study. So he introduced us to Dr. Aru Senayan, a cancer researcher from Michigan. Actually, he's a PI of the EDR network. And then he has a very good data analyst, Yuping Zhang, who I couldn't find a photo of her. So they already have this paper already published this paper in JAMA. At the time, it was an ICAP paper. And we said, can we stress test? Basically, we redo the analysis following the PCS pipeline, see whether we treat the same conclusion. So they were very brave, and they were also very confident. And they said yes. So we started working with them. They already had the paper. So this is a stress test, use PCS. So what they had in the paper was using 54 gene expressions, which they work on their past work, clinical variables, and they're predicting clinical significant, more serious prostate cancer. These are the people who are being subject to prostate biopsy. And they have validation cohorts. I will only report 1, but we also tried the other one. This is the external validation, it's kind of stability analysis. And the EDRN cohort is held at Hutchinson Cancer Center. So the researchers, now part of our publication, is being almost accepted. We only send the codes over and data processing. We don't touch the external data. So this group has been working on prostate cancer for many years, and they have My Prostate MPS 1, and this is MPS 2, right? This paper already published in JAMA this year. So they used logistic elastic net and find 17 more genes. They always include the KLK gene because this is a well-known gene behind PSA clinical tests for prostate cancer now. And they reached very good results, right? So they, among men who already set for biopsy, because this is the group people were targeting, the AUC for the original, like current method is only 60%. And there's another method, 65, 66%. And their early method is 74%. And this new method reached around 80%. So you can see the AUC curve. Okay, the plus means you use the prostate volume. It's not always available. So we have 2 versions. Plus means you use the prostate volume. The other, you don't. So this is a huge increase, even from their previous method, 7% increase of AUC. Okay, so we talked to Yuping, Tiffany, Anna, and say, could you have cleaned your data differently? Because she had to make judgment calls to know which threshold to take. So she She said, yeah, I could have done something different. With the time constraint and resource constraint, we worked with her and did 3 other ways to clean the data. And then we followed the PCS framework. We introduced more models. They were only using ElasticNet. We said, why not lasso? This is all like L1 penalized or ridge penalized and random forest and so on and so forth. So we have some new tree method called fix from my group. So we introduced 6 more. And then we screened, deleted 2 methods. For one reason is that one just didn't perform very well, the other because there's no importance score. We want to rank them. And then we use average ranking to select the genes. And then we look at subgroup accuracies. So here's the result in terms of data cleaning impact. Overall, data cleaning uncertainty between 1% to 2%. And I got it wrong. It's really should be 7 compared to, that's not right. It should be, the improvement is actually 7 to 20% improvement. Sorry about that. Yeah. So the first block, let's look at this plot, right? So on the right, you have names of the methods. Actually, we had 9 methods. And the first 4 lines are the kind of variability. I think we used the validation set to see bootstrapping the validation set. And the base is what Yuping used. And then the other 3, we have different thresholds. I won't have time to give details. She could have made different choices. So you can see that on the validation set, you can see the elastic net, it's pretty stable, right to 1% to 2%. And logistic ridge, it's pretty good too, actually. Logistic lasso, it's pretty good. And we have RF plus, it's a new method, adding this PCS overlay and many other things, adding also featurization to random forest. So that's pretty good too. And logistic, it's okay. Random forest, not bad. And roofit, it's not a little worse, so we decided not to cut there. That's a human judgment call. And then for roofit and also XGBoost, we don't have as good importance measure. People use a lot, so that's the reason we don't use it. And fix don't work really well, right? It's the last group. Okay, so we end up with about 6 methods. And then each of these methods has an importance measure, right? Logistic use the coefficients, and the RF plus, you have importance measures. RF plus actually have MDI plus, so you can rank them. And we took average ranking, right? We have the one who had the top ranking, and we went back to elastic net, use the top 1, top 2, top 3, top 4, so on and so forth. And then we end up finding 7 genes because we always use the KLK gene, and we reach very similar AUC. So what's the value added? One method actually could not get to 8 genes. My intuition is that the different, even linear method, because the penalties, handles the dependencies between these gene expressions indifferently. So if one gene is ranked very high across these different methods, that means it's more likely to be more important or possibly more causal. This is possibly, it's not the proof. And therefore, it's more important.
Professor Yu, we have another question from the audience. What
Yes.
method is used to measure the data cleaning uncertainty?
Oh, we use the AUC, right? AUC. Right, all this. AUC is the metric, and certainly we just bootstrap the data. So we fix the method, and this intervals from the bootstrap validation data. I think it's 95%. Did I answer the question? Yeah.
I'll
So the
let you know-
magic,
I'll let you know if another question comes in from that participant. I have another question. So all
Yes.
7 genes were stable in the 6 models?
more or less, look at the average ranking. Yeah, there's one difference type of thing. The order is a little different, but not hugely different.
Thank you.
Yeah. And if you take fewer measures, you basically get the same thing, but there might be one gene like got changed. Thanks for the questions. So with one election, actually the group before we joined them try to reduce, because for any clinical use, the fewer genes you use, the less cost, the more likely to be approved by FDA. So this is really the idea, like talking to different doctors, good doctors, and aggregate. It's really that idea. One method proof could not get to 8 genes. And then we work with the Hutchinson Center to look at the validation, right? We do lose possibly 1 to 2%, but with the 1 to 2% data cleaning uncertainty, this is within the range. So we think even the cancer research agree with us, this is very good. We call simplified MPS too. And we can do 7 genes, we can do 8 genes. You can see there's a little difference, but basically we're within the uncertainty introduced by the data cleaning. And now we're actually co-inventors of a patent, because our collaborator has a startup, and I'm very much in hope that this will become a clinical use in the future. So they really like this because it's a substantial reduction from 18 genes to 8 genes, and it's more likely to be approved by FDA. I talked to my friends from Australia. They say like their lawyers for cancer detection want 5 genes. So you can see there's a cultural difference, a judgment call. 8 for them, the lawyers say that's still too many. But in the US, my collaborator believe that 8 is kind of simple enough. So let me just mention a little bit about a much more complex project, which very much guided by the PCS framework tool. It has been ongoing for 6 years. We're still revising the paper. This is a very serious development, finding epistasis interactions for heart disease. So it's a general pipeline development, not just a method. And it's really a scientific recommendation system. Use stable ranking with tree-based method. We don't do linear method. We do a little bit in pre-screening, but then we use tree-based methods. And we did experiments and lots of domain knowledge. This project started in 2017 when we wrote the proposal. So I'll call out the main contributor. The first phase was actually try out for a simple phenotype. Well, simple is a human red hair, because it's much simpler than this heart disease. And the person with the tie, Ewan Ashley, has been my main collaborator. He's a cardiologist from Stanford, and the guy with the white coat, James Priest, used to be at Stanford, now with a startup leading a research. I'm really hoping that I just talked to him yesterday, that whatever discovery turned to be drugs. So he's very interested to help take the next step, maybe to see whether we can develop something to other drug. And 2 young, bright researchers, Qingru Wang, who's still a postdoc with Ewan, and former student, Tiffany, now Notre Dame. Tiffany, I mentioned already. So the heart disease, in terms of problem formulation stability, when we wrote the proposal, we were looking at another heart disease. We couldn't see any signal. So we end up doing this HCM, which is an expert area of Ewan Ashley. So this is a heart condition, happens in 1 to 500 people in the US, called hypertrophic cardiomyopathy. And if you have this condition, you have thickened heart wall on the left ventricle chamber. And previous research showed that cell size is associated, and there's an important genetic component to it, right? So that's what we did. We had to reformulate the problem, actually. The labels actually was very noisy, didn't yield any signal. So I just want to give you a high level, the complexity of this process. It's a multi-step evidence collection process. I think for a lot of complex human diseases, that's what we have to take. Statistics is only 1 step. It's not enough. The signal is too weak. We cannot really claim anything based on statistics, but we can be useful in this multi-step process. So problem formulation, we basically have to go back to use deep learning to get the size of the heart and left ventricle heart wall. Because the label from UK Biobank was very noisy. Too many people probably had the problem, was not labeled. We couldn't beat 50%. And then we developed a method based on our E3 random forest, because this is very low noise compared with the previous Drosophila case study we did. Signal was much clearer, and also previous red hair case study. So this epistasis or nonlinear interaction genes is very much at the frontier of functional genomics, especially for complex human disease. We did pretty well with GWAS, which is single gene importance, but most times many genes act together and the signal gets a lot weaker, and we need more sophisticated methods, and we need stability. And we did tons of annotated database. We did gene silencing experiments, so we became a recommendation system. And we did tons of work for mechanistic interpretation, use more data analysis and extra data sources. So we really try to use PCS towards causality, right? We know that predictability follows from causality. Stability is very much at the heart of causal inference. If you look at Sutova, right, that's the definition from Neyman Ruby model, the simplest case. We're basically assuming a lot of things away, saying things are kind of stable. You have one version of the drug, right? And then there's no interference. So you're saying there's one version of the outcome instead of multiple, depends on who else you're talking with. So it's really heavily embedded in causal inference. And there's an invariance principle, right? Saying that if something seems to be correlated with the outcome under different environment, this comes from econometrics in the 40s, then it's probably causal, right? So we're using this PCS towards causality for hypothesis generation and recommendation experiment. To compare with the traditional causal inference, this is not confidence interval CR, and the observation data, here's a comparison. Traditional causal inference observation study don't do usually model checking. I think that's something we need to do. You cannot pull out causality, even with all the assumptions you say kind of valid without model checking. There's a quantitative checking aspect we do through prediction screening. And causal evidence in traditional approach, basic domain knowledge. I always find it hard to see the arguments. There's not a lot of extensive documentation about why there's this identifiability assumption, why you have an instrumental variable, why you can have a mediator. I always find it very uneasy when I read the papers. I just felt like, why do I? Because the conclusion so much rely on the assumption. So we do stability analysis to weed out confounding factors. And then we recommend experiments. We don't claim we are a recommendation system. We don't claim causality until you do interventions. So this pipeline is, we do 3 split, we did random split because the people data bank is already, they already take away people with families, all of that. So it's pretty much not very dependent. And we use domain-inspired dimensionality reduction to prioritize our SNPs. And we have a very important step of stability too. We binarize the heart, like left ventricle wall size, so that we know if we beat 50%, we have a signal. Otherwise, we don't know whether we're just fitting noise. And we did a lot of stability through random forest because the tree structure matches well with the biomolecule interaction at the cellular level. And we did experiments, and we did more using other data as well after the gene silencing experiment. So here's the summary. We did 5 sets experiment. We were very engaged. It's another talk to do the detective work to find some problems with their sorting, and the redid experiment. That's another more like shoe leather work. We did 5 sets experiments and 4 successful. In particular, we found 2 epistatic interactions, means non-linear interactions between CCDC, which is very close to a very important muscle gene called Titan, and then CCDC and Titan, and then IGF-1R is a growth factor. Titan and IGF and CCDC were next to each other, but they actually have different functions. People thought maybe they just work together. Actually, they have interactions, depends on other situations. And it's a huge amount of work. And the paper is still being reviewed by Nature Cardiovascular Research. The first response we wrote for the first round of reviews was 38 pages. So that's why I called James to say that I hope there's a drug, so much effort put into it. And he said, yes, we're interested in looking into it. So what are the values added? It's really high yields for follow experiments, right? For the first paper with the RF, we had 80%. That was Drosophila. People did experiment before, like traditional experiments. And here we have another 80% high yields. And we tried all the conventional methods. This is a very PCS project. We tried all the other conventional methods suggested by reference, so it's pretty thorough. We could not see another pipeline. But of course, we didn't do the gene silence experiment for those suggestions, but based on annotated database, they were not as meaningful for the top ranked genes. So this is some evidence that was the right decision to follow the PCS pipeline. And now collaborators really didn't push back at all. So why didn't you use, they had complete trust in us to use this new method because the principles make a lot of sense to them. They work at the code surface, they know the problems. They want stability. So to finish, I'll be very quickly, chapter 13, study on uncertainty quantification for regression, was written with Baker, but now have new team people try to do more data results. I'll be very brief. Michael's a master's student, Abby, PhD student, Bao undergraduate, Omar PhD student, both actually, Abby and Omar will be graduate, they're both fantastic. So if you talk about uncertainty, we have to start from what we mean by the probability. We often just quickly go to the probability framing without really articulate what we mean by the probability. Without that, p-value doesn't make sense. So we try to include data collection process and data cleaning choices and modeling choices. So the mentality or the spirit is very similar to Bootstrap. Doesn't matter what the story you tell yourself. When you use Bootstrap to do uncertainty quantification, you're actually very concrete. You're assessing probability relative to this collection of pseudo data sets with Bootstrap samples from your original data, and you're assessing probability relative to that. That's what it is. All the calculation based on that. You can come with other stories to justify, but effectively the calculations relate to that very concrete collection of possible data sets. So in that spirit, we do the same. Except that we worry about data cleaning. So we expand the pseudo data sets and different methods. We end up with very concrete pseudo sets of things we're comparing the probability. The meaning of probability is defined. And you write a document that say why that universe of pseudo data is relevant. So you need to have a data documentation to back that up. That's the interpretation probability. And conformal inference has got a lot of attention. Let's just compare with conformal inference. It's a one method approach, more traditional. Doesn't worry about data cleaning. Use one machine learning method, we allow multiple. And we do prediction check. Some current work, actually, younger people are trying to bring the prediction check into the conformal. That's really great. And we perform local calibration. So we both have a calibration step. The way we get to the correct coverage is through multiplication. So it's kind of, if you have a small interval you start with from the different Bootstrap predictions, from different good algorithms and from data cleaning, you keep that, you multiply. So if something has small interval, you have. And for the conformal, it tends to be, they use constant. And we scale length, as I said, and instead of constant. So that's the difference. So we compare with 7 data show. Actually, we have now about 15 data sets. I need to update my slides. Overall, for low dimensional problems, we reduce the length from conformal by 30 to 50%. Both have good coverage because they both calibrated. And for the high dimensional data set, we don't reduce as much. We reduce by 5 to 15%. And the good discovery is actually nice for us to has good desirable subgroup coverage. and conformal because the constant length cannot adjust to subgroups. The intuition is that when you have lots of data, on average, usually have very tight coverage. All these different perturbations give you very similar, so you have short. And when you calibrate, you keep the short coverage. So this is really indirect reflection where the data are. So for that, I will finish. And there's a very nice review written by Yuval Benjamini with a nice note officially. And we have mentioned you have internal validity, uncertainty quantification, recommendation. You can do stress testing, new methods, and extensions. And we're working on things with colleagues for large language models in medicine. And just mention that the papers has been put on archive to say that large animal development, everything is apprehended because so much black box. We don't know what's data. We don't know the problem formulation actually is generative. So it's supposed to solve many problems. And we really hope some of the labs will really open up their process, at least to a committee of oversight who can answer these questions. So we have some software, which is code check called vFlow to help PCS style analysis to make the stability easy. We also have an R package called SimChef to make multiple simulation. That's stability for simulation. You should not simulate from one model, you should simulate from multiple models. And merits, that's what Nancy was asking called. It's a simulation guidelines. And we sent to JCGS, they really liked it, but they said they want more examples. So working on that. And this is, we define you need modular. You want your code to be modular in self-contained logic partition segments of code. Also, you want efficient, streamlined computationally and conceptually. You want realistic, so you have to check reality, faithful to the physical world, and intuitive, so that people can assess whether it's responding to reality. And we need transparency for documentation, and that's for stability. You need reproducible, replicable, and externally validated. So that's where we have, Corinne has been leading this. She just graduated to work for Berkeley Consulting. It's a great name, merits. We call SimChef. This is the package. It's like you're cooking, right? You want to be a good chef. And we have a documentation you can use as a template, help especially for beginners to streamline the process. And I think I have too many. That's the papers. Yeah, that's the papers. Thank you.
Okay, well, thank you so much. I do have a couple of questions that have popped up in the chat and the questions. First, does your book contain any guidelines or examples on how to document the data cleaning process, which, as you've said, can consume 70% of the total effort?
Yes, it's very detailed. We have action items. We have validity, missing value. It's very detailed. Yeah, you can easily turn that into some package for your field.
Great.
Yes.
Okay, another one. How many different perturbations or scientific analyses constructed on differing versions of the data set are recommended for getting a good estimate of uncertainty in PCS? Is there a general rule of thumb?
We do something like 5 to 10 because of the resources, and at least 2, that's my recommendation, at least have 2 cleaned versions, and we usually do 5 to 10 right now, like 4 to 10, just because of the resource limitation.
Do you base that on the scenario at all, or just the resources?
It's about resources.
Okay. Is there a chapter in the book on PCS for survey statistics?
No. So this book is very general, and I'm working with, through my student Zach, with a group in social science, try to really, there's a whole field called, people use in social science quite successful, called multiverse. So we try to combine the two for some guidelines for social science, like decision-making. And it needs to be unpacked with a different subfield of statistics. It will be more useful. So if you're interested, you can just, I'm happy to take a look when you unpack it, but it needs to be unpacked more in detail for a specific field. And we do actually mention that we did run a Veridical data science conference with Stanford, Berkeley, Stanford in May. If you go to my website, all the talk videos are there, and was really successful. So I'm taking the machine learning people in EPFL in Lausanne. It's going to run one in Europe on June 23rd, 2025. And 2026, we're going to return to the Bay Area to do it in Stanford. That's the plan. But the one with Lausanne is confirmed. I'm not running it. I'll probably attend, but it's by the machine learning people. And there's one person from statistics on the committee too. So that's June 23rd, 2025. If you go to my website, the workshop videos link, you'll find that. That was last May. It was really well attended, and everybody really enjoyed it. We have people from medicine, not just PCS, it's general about reproducible research. And my talk, if you go to Simons Institute, you can see, I will show you the link. There's a very nice workshop going on right now on alignment, trust, and watermarking. Let me.
Okay, we're not seeing your screen anymore. Are you?
Yeah, I'm just
okay,
looking for.
Okay.
Yeah, yeah. So. Right. So Simons, actually, I became a scientific advisor at Simons. It's great workshops throughout the year. So just have a habit of going there. You can attend on Zoom. So this is going on right now. And my talk is on Wednesday tomorrow. You can see I'm talking about vertical data science alignment in medical AI. And we had a great panel on AI regulation yesterday. Yeah. So very workshop. We have great workshop. We have the large language models through the whole year. And then there's also like a new paradigms in generalization, more machine learning. So 2 programs going on. You can go look at like workshops and symposia. You can see all of that. This is going on. And there's also something going on with quantum. And this is very interesting for machine learning domain adaptation. And there's unknown futures. And you have reunion, people do the database, and you have neuroscience and large language models. So it's really, you can attend online. So this is just a shout out for these great resources you can attend.
Okay.
At Simons Institute at Berkeley, yeah. Yeah.
Okay. I had another question for you, and and I've got a couple more in the chat. Let me do those first. Do we see an extension of the approach beyond medical classification, identification, or prediction? Will there be a practical application there, e.g. climate modeling, uncertainty impacts property, and causality risk models and insurance premiums?
We haven't done that, but I don't see any reason that cannot be used as guidelines. It's a general framework. We just haven't done the case study because it depends on my collaborations.
Here's a good one, it's somewhat philosophical. Does your work talk about a minimum level of uncertainty that's inherent in scientific research that could be relevant to policymakers or politicians who want to claim that scientists are failing by falling short of predictions?
I feel like that question should be discussed together with policymakers and the people working on policy domain. We can it's going to be a human decision by committee to say, I would say that at least I would suggest minimum, you should worry about at least 2 copies of clean data to see how your policy recommendation change. I would call that the minimum requirement. And 2 methods, at least 1 more. Because we have so many supervised learning methods. And depends on how you choose one, as I showed in this from other fields, you might have different conclusions. So if you want to go beyond 1, the minimum will be 2, right? But maybe you want to do more. So you could go to 5. If you look at the field, in particular policymaking, people commonly use 5 methods, I'll make that 5. But without knowing the domain, I would say at least 2. Or you say, this is the right method in physics, right? You might be able to say that. But I don't think in other areas we have that.
Well, my question was really around your comparison of the PCS with causal inference. So one of the ways that domain area knowledge gets into your modeling effort for causal inference can be through the design of the relationship. So if you do a DAG to specify your model and then use that as your justification of causality, those assumptions that are codified in the DAG. So that's, that kind of tells you the structure of your modeling effort. So that's how the domain expertise gets into causal inference. How is it getting into PCS? Is that?
Well, right there, you have a stability question. Two experts more likely might have a little different DAGs.
Mm-hmm.
Right, you should take that into account. Right, I would be very surprised, except at something like physics, all the factors. People just think a little, it's very qualitative. Yeah. Humans, we don't have precise causal models in our mind. It's very qualitative. And since, especially in social science, there are many factors at play. That's what I've told. You don't want to actually concentrate on a few factors.
So I suppose the PCS process could be wrapped around that whole process with an exploration of possible DAGs to consider in doing your causal inference.
Exactly. But that's why the book, and now the book is out, so hopefully people can evaluate it better. We have a project try to go that direction, but I'm only one group with limited resources.
Okay. Well, I think we've gotten all the questions, and I want to thank you for a really great talk today. I think this is going to be valuable to increase reproducibility. People follow the process here.
We very much hope so. That's why we spent 9 years to write a book.
Yeah. A worthy effort. There's lots of non-reproducible things out there. So thanks to our audience, and
thank you.
Have a great day.
Thank you.